Okay. Good morning, everyone, and welcome this session of the EDP and Applied Mathematics Seminar. It's an honor for me to introduce the Professor Luis Yapu, postdoctoral from Fluminense Federal University. On this occasion, Professor Luis Yapu will give the lecture entitled Optimal Control of Chemotactic Gains in a Logistic Keller-Segel Model. Welcome, Professor Luis Yapu, and you can start.
Okay, thank you. Thank you very much, Professor Juan. Thank you for the opportunity to the organizers of this important seminar. This is a joint work with Professor Yacuba Simpore and Professor Enrique Suazua at FAU University, Friedrich Alexander University in Germany, and Professor Mahamadi Warma in George Mason University in the United States. This is a work about chemotactic systems. So let's start. What is a chemotactic system? Well, chemotaxis is a phenomenon where we have two populations. One population of cells and one population, let's say, given by a chemical, some density of chemical, and the chemical has the property that it can attract the cells or repel the cells. So depending of the gradient of the density of the cells of the chemical, we have that property. So this is chemotaxis, and the Keller-Segel model is let's say the most important, most model for that phenomenon. The model, we work in 2 dimensions. Omega is a subset in 2 dimensions, and this is the model. V models the density of the chemical, and U models the density of the cells. The model of V, the equation of V, is a Het equation with a decay with rate alpha, but also the cells U cause the increase of V with this term, beta U. And now the equation for the density of cells has a diffusion term also. We will add a term in the right-hand side, which model a logistic term, which allows us to control, because it's known that this kind of model have blow-up phenomenon. So in that case, the logistic term helps to control that. And the nonlinearity, the relevant part of this model is this term, where we have the density of V, so the density of the population of the chemical will transport or convect the density of cells U. This is a vector field, and we have here an equation of transport equation for U. And now we will add a function f, which is here, and it will be f, our control variable. So we will try to modulate to control here using that function. So this is the, let's say, the novelty of this work. Okay, I think I have said that. There are some studies also in the medical literature where they state that the controllability of the sensitivity, that function f is important. So it could be interesting also in applications. The basic works we use it to do this work are those ones which are already optimal control, but here this is a distributed control, not bilinear. This is the problem that since we are working with density of populations, so we can't have a negative density. So it's better to work with a bilinear control. So this is the other works. Here they work with a bilinear control. And okay, so with the bilinear control, we can keep the property of having positivity of the densities. We will control in our case with this function f, and our cost functional is given by those terms. We will compare with some function along all time. So we have that interval. We have also, we'll control the L4 norm of the control f. It's also possible to control the final time and this quantity. So we try a more general cost functional with this form. Okay, which are the main results? I think there was okay. We will work with the controls will be in this set in L4, but we will the condition that the controls are between two functions, xi1 and xi2, which are L infinity. And first we'll define a solution of our problem. After the study we have done, we found that we will work with this space for U, the density of the cells, L infinity L4, L2 H1, and for the chemical, these spaces, those spaces. Okay, so this is the initial conditions, and we will work the first equation in the weak sense and the second equation pointwise. So this is the notion of solution that we will use for our problem. The first result is the existence and uniqueness of the solution. So starting with these initial conditions for U and V, positive, no negative, there exists admit a unique solution UV which are positive, which is positive in the spaces we defined it just before, and we have the control of the norms. There exists a constant, and we have this control with a constant k depending only in those parameters of the system and initial conditions. So this is a unique existence and uniqueness result. How a problem that we have with that model is that the equation here maybe it will be clear. We will need to regularize of the equation. Yeah, here I think we can see. The problem is that we have those kind of terms. This was a square, U epsilon squared, and we will use a fixed point argument. But the coefficients here, this is a linear equation now. This is linear, but the coefficients are not bounded. So we choose it to regularize with this function a epsilon. So now these coefficients here appearing are bounded, so we can use more standard results. This is now this is the regularized system, and we will show that there is a solution of this equation, and that afterwards that we can pass to the limit when epsilon goes to 0, and the estimates we get are independent of epsilon. Okay, so this is the linear auxiliary system. The system 4 is linear with bounded coefficients. Okay. Donc, the auxiliary system, regularized system, Okay, this is the map, the fixed point map. We want to find a fixed point of this application, and a fixed point of this application will be a solution u epsilon v epsilon of the nonlinear map, and then we pass to the limit where epsilon goes to 0, and using estimates which are independent of epsilon, we get a solution of the initial problem. So the study of the regularized system, since it's linear, we can use a standard maximal parabolicity results. This is a standard. Now we will have that the right hand side of the equation of u is in L4 is in this space. So those are standards maximal parabolicity results for u and v. So the point A is not difficult because the equation is linear. Then we have to compute a fixed point. We'll use a Schauder fixed point theorem. This is our set. We can show that the map R have image in the set SM also. And we have compactness using the Aubin-Lyons results. The spaces W14, W14, L4, and W minus 14. So we can use Aubin-Lyons result, and we get the compactness of R. And only now we have to study the continuity. I won't give all the details because there are many computations. We define the difference. Here this difference. Now we work with sequences, and we want to see that the image of a sequence is equal to the image of the limit of the sequence. And doing the estimative energy estimates with this difference W and Zn here, we can show that the map is continuous. The estimates are technical. I won't give the details here. So we conclude that there is a fixed point, and we have our solution. But now this solution depends on epsilon, and we have to show that there are uniform bounds. And this is this result which says that yes, we have uniform. We have bounds K1, K2, and K3, which are independent of epsilon. We also have the positivity and the maximal parabolicity result, all independent of epsilon. Here I will give some, I think maybe I will explain only this slide about some computations. We have to show the positivity of the solution. So we can state u epsilon minus as the negative part, and we will show that the negative part is 0 using energy estimates. So we take the negative part, we test the function, and we get this inequality using standard energy estimates, Cauchy-Schwarz, Young inequality. We get this inequality since the negative part at the beginning 0 was 0. So this implies, using Grunwald's inequality, that our solution is 0 for positive time. So our solution does not have negative time, so it's non-negative. There are also some other estimates. We have to pass from one space to another space. Always testing that we get uniform estimates on epsilon. we use the properties of our regularization function. This quantity can be estimated also independently of epsilon. So we have that a u epsilon is in L2 uniformly in epsilon. We test the equation with V epsilon and Laplacian epsilon. And we also get independent constant here of epsilon. So we gain a regularity in V. We continue the analysis using la Gallardo-Nirenberg inequality. We can control the norm here, L4 norm of the gradient, and it will be important. So now we have that this quantity is bounded independent of epsilon. Now we test the equation u epsilon. Okay, Ladisinskaya. Here we are estimating the right-hand side. Jung. And we arrive at this expression where we have the L4 norm of the gradient of V. And just before we saw that this is quantity is the integral time here is bounded. This one. So Gromwell inequality also allows us to bound u epsilon. So this is the kind of estimations we did. I think this is the last estimation, and we arrived to this to show that u epsilon is in L infinity L4. And once we have that u epsilon is in L infinity L4 is in particular in L4 time space here, maximal parabolic regularity allows us to find the equation of V, this estimate for B, independent of epsilon. So we have shown that our estimations are independent of epsilon. I won't give more details on the proofs. Now I have to discuss about the existence of the optimal controls. This is a classical in the statement, the result. We have for the existence of optimal controls, we have an admissible set of controls F. Is the same that I presented before. And it says that there exists a point which minimizes the problem. So first, we show that there is a solution. Before there is a solution, U and V, and there is this set F is non-empty. So this set S is non-empty. The functional J is bounded from below by 0. So we have a minimizing sequence. There is a sequence Sm such that this limit is the infimum of J, of the functional J in S add. Yeah, one term of the functional was the L4 norm of F. So also this shows that Fm is bounded in the L4 norm. We also have these estimates from the theorem of existence. Then we have that F is a closed convex subset of L4, which is weakly compact because L4 is reflexive. So there are subsequences. There are sequences Sn, subsequence, such that we have the following convergences. Sn is a triple, U, V, and F. UM, VM, FM. We have the convergence of U weakly in L4, also in this space. For V, the derivatives, all these spaces come from the first part of the existence result. And using O'Ban-Lyon's theorem, we can get those were weak convergences. We can get some strong convergences. We can do the product here with having the strong product. And this allows us to control the term, the nonlinear term, f u gradient v. So we have you can show that this converges. We have this convergence equation 33. Okay, this is here. We have phi is the function test. And we can pass to the limit. Now we can pass to the limit in the equation. So there exists the limit u tilde and v tilde here. Verify the equation. Since verify the equation, the value of the functional at this point is bigger or equal than the infimum. The infimum was attained by the sequence. On the other hand, since the functional is lower semi-continuous, we get this other in the other sense. And this implies that u tilde, v tilde, and f tilde is a global optimum. It's equal to the infimum. So this shows the existence of the optimal controls. And now we need a way to compute those optimal controls. And it will be given by the optimality system. Following the works I presented 3 works, preceding works. We also choose to work using a general theory of Lagrange multipliers. So in general, we have some functional and some abstract operator G between Banach spaces X and Y. This is the functional J. So we have our constraint, our PDE, and the cost function. We can associate a Lagrangian functional, and there is these covectors, these psi are these elements are the Lagrange multipliers. So we get the Lagrange multipliers. The psi is called the Lagrange multiplier if it verifies this condition. And for us, X is the spaces we studied in the first part in the existence, W4, X4, L4 for the control. Y, the operator is given by the PDE, the system, the first one, weak form, the second one, the second equation of the PDE. And we can use this general theory for our problem. So we compute the derivative of our functional, the directional derivative, in this case, really the Frechet derivative. And this is the expression, is a computation. We can also compute now, we need to compute the derivative of the operator, because here in this definition of the Lagrange multipliers, we need the derivative of J and the operator G. Those are our computations. Now we have both derivatives. And a general result, here there is a theorem. For apply the theorem, the existence of the Lagrange multiplier, we need that the point be regular in some sense, which means that it should be a solution of a partial differential equations. But at the end, we show that there exists, by a general result of Lagrange multiplier with regular points, there exists Lagrange multiplier, which verifies that this condition is really the translation of J prime and G prime. The proof of this theorem is, since we computed this, this inequality gives this big formula inequality here. And this theorem allows us to deduce an optimality system. The Lagrange multiplier is now the psi is lambda and eta, and verifies these equations. This condition, final condition, is because we have in the functional, in the cost functional, we have a term defining testing also the final time. And the optimality condition is this condition a bit complicated, because since the functional is in L4 norm of the control, we have here the derivative of that. And okay, so now we have an equation for the Lagrange multipliers, the dual variables, and also the optimality condition. And this allows us now to apply some numerical methods to solve a really concrete problem. For that, we defined an algorithm, an optimization algorithm. We have a final time t. We choose some time steps, initial data, the initial control and initial admissible initial control, the parameters of the problem. We compute, we do a forward step of the two equations, here I have written in this form. This is okay, this is the discretization in time of the first and the second equation, which allows us to find k plus 1 using uk and so on. Now that we have computed u and v until the final time, we use the adjoint system to compute backward in time using lambda k plus 1. We find lambda k. Same for eta k plus 1. We find eta k. This is the discretization also. And we have a complicated formula for the actualization of the controls, since because we had this degree 3 equation for f tilde 3. Here we have f tilde. It's an equation of order, an equation of degree 3, and that explains this expression for the actualization of the control. Then, so we have iterated u and v forward. We have iterated lambda and eta backward. We have updated the control, and if now we test if the solutions are, some conditions are verified. If not, we can iterate the process with this new control, and this until we have convergence. So this is the method. Yeah, in the practice applications, to solve the PDEs, to solve numerically the equations, the problem is that we are in 2 dimensions, so it could be very complicated if you use a standard finite element methods or finite difference methods. So we will work with B-splines. So this allows us to represent a solution as a combination of some splines, some basic functions, splines in X, splines in Y. The product will give us a tensorial spline in XY. And a solution could be a combination with some coefficients. So the objective now will be to find which are the coefficients. We have fixed a basis. And I think I remember that we used only 10, 20 bases, element of basis in x, y. So we have less coefficients to compute. That is why we choose it to work with splines. Okay, I think this part are the more technical details about the implementation. We have a partition. This is the discretization. I think the most important part is in this, well, the idea is to represent the solution. We have to compute the A, the coefficients A will give the solution U, the coefficients B. So here we will iterate, we will find some minimum, we will minimize a problem, and we will find a minimizer A. Those coefficients will define the solution U. And we will do the same, we will minimize some function B, and it will give the coefficient, and we will define the solution B, the equation of B. Set here. Okay, so this is the method. That is why we use spline. And as only here as a numerical example, I start with some Gaussian U and V. This is a Gaussian. I have a desired target UT. Is also a Gaussian centered in another position. Our set is 0, 1, 0, 1. We are working the square. Okay, we use so those are the U0, this Gaussian U0. This is the Gaussian V0. After t half time, we have the solution U for U. And at the final time, we have this form for U. So this is only an illustration of the method for this toy example. In the paper that we are working, we are finishing we will present more examples, more interesting examples. Okay, for future work, it could be possible to find maybe vector or matrix controls, because here in what we did, we take our control was only a scalar function f, which controls only the magnitude of the vector, because we are multiplying a vector field, gradient v, by a function. So we are controlling the magnitude of the vector field, but it could be interesting to work with a matrix also, with a matrix of controls. In that case, we have maybe more possibilities in the controls. And also we can have more numerical study, convergence. Okay, more theoretical numerical study. Okay, it's all I wanted to say. Thank you for your attention.
Thank you, Professor Luis Yapu. Any question or commentary? Oh, I have a question. Oh, Yapu, numerical simulation for the equation to the study?
Yes.
Yes. Your domain is limited. The problem in unlimited domain is possible?
The domain omega is limited. You mean the case unlimited domain about the domain? What
Yes,
is
yes,
the
yes.
question?
Is possible studying your problem?
Uh, our theoretical results are only for finite domains, bounded domains, and the numerical part, it's also in bounded domain. So we don't have any results in unbounded domains. No, no.
Yes, yes. Thank you. Other question? Other question or commentary? Spanish, Portuguese? Well, if no any questions, thank you very much, Professor Luis Yapu, for your excellent talk.
Thank you very much. Thank you.